Swayam Prabha. Digital India. Educated India.
Welcome back. We are discussing about solid propellant ingredients in the context of solid propellants. So far we have talked about the different types of fuels used in solid propellants, different types of oxidizers like the inorganic oxidizers, the organic oxidizers like explosives. So, in terms of inorganic oxidizers, we have talked about the nitrate based oxidizer, percolate based oxidizers, and there we have also talked about that the ammonium percolate is considered to be the workhorse oxidizers, because that is the most commonly used oxidizers in solid propellant rocket, and due to the high performance this oxidizer is preferred. Although there are some issues related to the products coming out from this type of oxidizers, for example, like chlorine substances, chlorine related compounds like HCl. However, the ammonium perchlorate oxidizer is very common for solid propellants. Then we have said that since both the fuels and oxidizers are solid crystals or even solid particles, if we talk about the metal particles as fuels, they are solid spherical particles, whereas the crystal oxidizers are solid crystals. So, we need to have some kind of a glue in order to hold them together. So, binder takes care of that by holding fuel particles and crystalline oxidizers to form that matrix and to give the structural glue. So, we have said that the various polymers are used as binders, and they are mainly the polybutadienes, and we have said that the modified ends of the polybutadiene molecules, we can have like hydroxyl terminated polybutadiene, which is kind of a common binder used for solid propellant, or it can have like carboxyl terminated. Okay. So, let us look at their formula very quickly, and then we will move on to other ingredients. All right. So, we have written that earlier that the very common binder is HTPB. So, we have said that it can have like polybutadiene. So, many of them are like in a group, butadienes in a group. So, if the polybutadiene chain attached with some kind of a polyacrylonitrile group and acrylic acid group, they are going to form PBAN. It is called polybutadiene acrylic acid acrylonitrile. So, the acrylonitrile group will be like CH2 CH or it can have like acrylo. So, carboxyl and nitrile groups get attached to the butadiene chain to form, it is highly cross linked chain network. So, PBAN is kind of linear and cross chains, and it gives lower tensile strength with smaller elongation. There are modification of these carboxyl groups in PBAN, and making them towards the end, it gives the better mechanical properties. So, the modified version of the polybutadiene is like carboxy terminated polybutadiene, which is CTPB. So, this gives better mechanical property. Better mechanical property means it can give the good quality of the binder, which can hold the crystalline oxidizers and fuels better, and it will going to give the improve the mechanical property of the grain as well. So, that is one of the common oxidizers which have been tried. The other the most common one, as I said, is the HTPB, and of course, PBAN is also the common one. So, HTPB is hydroxyl terminated polybutadiene. So, the polybutadiene chain will ends with hydroxyl radical. Now, this is widely used in the manufacture of composite solid propellant. Now, the molecular mass is going to vary depending on the how many chains are present there. So, typical values of the molecular mass can be it can vary from like 30,000 to even 1 lakh kg per kilomole. So, that largely depending on the polymerization, the degree of polymerizations, which is going to tell us that how much molecular weight is there. Of course, we in order to have like a higher molecule, we need to have like a higher dense HTPB polymer in order to improve the volumetric loading of the composite propellant, and of course, we need to have like a better mechanical property of the grain as well. But the preferred choice of the polymeric fuel or polymeric binder is the HTPB. Other than that, PBAN is also used as the binder for composite solid propellant. But of course, the high performance of the HTPB is preferred for wide application in composite solid propellants. So, basically the role of the binder to give the structural glue of the fuel and structural glue for the propellant grain. Propellant grain means which containing the fuel, metallic fuel as particles, the crystalline oxidizers, for example, like ammonium perchlorate, fuel as aluminum particles. So, the binder will give the structural glue to hold those solid particles in the composite propellant matrix. Okay. Now, what are the other ingredients? As we said that the fuel oxidizers, binders are the major ingredients. In fact, if we even do not need the metallic fuel, if we only use the HTPB plus AP, it can still work as the propellant, because the HTPB will act as fuel as well as binder, and this is the oxidizer. So, if you recall, we used to draw this picture like if you initially the HTPB is just like a liquid. So, if you add the AP crystals and make it a form of, let us say, this type of a strand or small pellet, and if we ignite this, if we inhibit the outside surface of the propellant and if we let or allow to burn from this surface only, it will definitely going to burn, because it is containing the oxidizers, it is containing the fuel. So, here the fuel is the binder itself, HTPB will act as fuel and AP will act as oxidizer. So, the principal ingredient must be like one fuel and oxidizer, one fuel and one oxidizers, but the fuel as per the rocket literature, the fuel are considered as the metal fuels, and we are talking about the binder separately, because binder is providing the structural glue or binding the solid crystals like Ap and the metallic fuel. Otherwise, if we do not use aluminum or boron particles or barium particles within the propellant grain, it is still going to work because the binder will act as fuel. It is hydrocarbon, so it is going to burn. So, this is the most common ingredients, the fuel and the oxidizers. Now, there are several other ingredients which are also used, and according to their use they have this different functionality. For example, like curing agents. Curing agents role is to cure the uncured propellant, means once we have this mixture of the fuel, oxidizers and binder, we need to form the matrix. So, this pre-polymer which is going to be form a cross linking and make sure that it is going to hold the solid crystals within the propellant matrix, the one kind of agent which is called curing agent, which is going to accelerate the curing process or cross linking process. So, the curing agents will act as an agent for accelerating the cross linking, and is going to form the cross linking of the polymers, which is going to hold the solid crystals. So, it has important role, although the amount of curing agents may not be very high, maybe like it may vary from 0.2 to 3%, but it has very important role to play in order to making the cross linking. Similarly, like plasticizers are kind of low viscous liquid. They are going to improve the processing property of the propellant. Like sometime if we put too much of solid oxidizers within the propellant matrix, like we add 70 to 80% as the solid oxidizers. So, sometime processing is going to be very difficult, because we need to mix it thoroughly, we need to pour it, because after mixing our next job is to we need to cast it, we need to give a proper shape of the grain. If you recall, we said that there are various type of perforations can be tried, which is called grain configurations. Now, it can be cylindrical, it can have like a star shape, it can have wagon wheel, it can have multi-hole. So, depending on the requirement of the thrust time profile or pressure time profile, this burning surface area, initial burning surface area will be designed or will be decided. So, this initial burning surface area is called the grain configuration. So, the next part of the propellant processing, after mixing, we need to give that shape of the propellant grain or the internal perforation of the propellant grain. So, we have to cast it within the mold and mandrel. So, this is the mandrel and this is the mold. So, that is giving us the type of perforations we are having from the grain, within the grain. So, in order to cast this, we need to have some certain processing properties that we need to pour it, we need to pour it within the casting system or where with the mold and mandrel is. So, the plasticizer is going to reduce the viscosity in such a way that it will improve the processing properties. Sometime it may actually lead to long pot life of the uncured propellant. So, it will remain as slurry, it will not start becoming solidifying, it will have some fluidity which will improve the processing property of the propellant. So, the plasticizer has important role, although the very low percentage of plasticizers are used for such kind of applications. We can get different examples of plasticizers like dioctyl phthalate, DOP, dioctyl adipate as the common oxidizers used for plasticizers, common plasticizers used for solid propellant. There are various curing agents have been also been tried like IPDI, TDI, toluene diisocyanate, then there are IPDI, isophorone diisocyanate. This is like isophorone diisocyanate. this is toluene diisocyanate. They are act as curing agent. They are of course used in a small quantity just to act as cross linkers to so that it will cause the prepolymer to form longer chain of larger molecular mass, and is going to interlocks between the chains. So, it is going to cure the propellant. It will help to cure the propellant. Propellant means it is a mixture of binder, oxidizer and the solid fuels. Now, of course, the minor change in percentage of this type of curing agents may actually change the physical property. So, as I said that it may be used like 0.2 to 3%, but minor percentage change may actually change the physical properties. It may change the manufacturability of the propellant, or in fact, it may change the aging characteristics also. So, depending on the requirement, it can be used. So, they are only used to only used with composite propellants, because this type of curing agents is going to help to make the propellant mixture solidify and become hard. So, it will have common application in composite solid propellant. Now, in case of plasticizer, as I said, they are low viscosity organic liquid or organic ingredients, which is basically a fuel also. They can actually burn, but they are added to improve the processing properties. So that the viscosity, sometime it may lower the viscosity, it may actually required for casting processing during the transfer of the slurry to the mold and mandrel system, so that it can improve the casting process. It can actually have a longer pot life. It can help to have longer pot life of the mixture ingredients, but they are uncured propellants. Various type of plasticizers, curing agents have been tried. So, the participants are requested to refer to any kind of rocket textbook. It is already listed in the syllabus as well. They can actually get many examples of various curing agents or cross linkers which can react with polymer and form like long chain. Similarly, they can get example of the plasticizer as well, like DOP, DOA. There are different burn rate modifiers which have been tried for solid propellants. So, they are basically either accelerate or decelerate the burn rate. If we have certain ingredients of the propellant within the matrix, either they can increase the burn rate or they can decrease the burn rate. So, the role of the burn rate modifiers, as the name suggests, it will modify the burn rate of the propellant. There are certain catalysts which can actually accelerate the burn rate. For example, like Fe2O3 ferric oxide catalyst, which can sometimes act as the burn rate enhancer. There are certain category of burn rate modifier which can actually decrease the burn rate also. So, we can have like Fe2O3 or ferric oxide, which can actually increase the burn rate. There are some other type of burn rate modifier which can actually reduce the or inhibit the burn rate. Lithium fluoride, for example. So, depending on the applications, we can actually either have like accelerating type of burn rate modifier or decelerating type of burn rate modifier, but of course, they are also used in a smaller quantity. Again, as I said, like depending on the functionality, they are used or they are not used. Okay. But there are number of different ingredients which have been tried for different solid propellants, and they will definitely they will definitely have the different functionality. So, based on the requirement, there may be like 200 plus ingredients which have been tried in a solid propellants. Okay. But the major ingredients, as I said, the fuel, binder and the oxidizers, and there are some other ingredients like curing agents, plasticizers, burn rate modifiers, etc. And to have other functionalities in the propellant, there may be number of additives which are used as the ingredients. Now, have some discussion on the various type of ingredients. Now, let us talk about the classification of solid propellants. So, mainly the solid propellants are classified into two. One is called the homogeneous propellants and heterogeneous propellant. This is based on the mixing properties of the propellants. So, homogeneous propellants, as the name suggests, the ingredients are intermediately mixed, whereas in case of heterogeneous propellant, the propellant ingredients are not intermediately mixed, rather they will coexist together, and you can individually actually have the properties seen individually, they are not intermediately mixed. For example, like if you have solid crystals mixed in a polymetric binder, you can have like heterogeneous propellant, whereas there are other ingredients which can actually intermediately mix together and form homogeneous propellant. So, based on this homogeneity and heterogeneity of the propellants, they are categorized into various categories. So, we will talk about that, and based on the other functionalities, there are different types of propellants. For example, like they may be igniter propellant, there may be gas generator propellant, there may be like reduced smoke propellant. So, we will talk in detail little later. Let us first talk about from this perspective of homogeneity of the propellants. So, they are actually mainly homogeneous propellants mainly are termed as the double base propellant. So, the primary ingredients for double base propellant are the nitrocellulose NC and nitroglycerin Ng. So, they are mixed together at molecular level to form the homogeneous propellant. Now, the NC or the nitrocellulose, they constitute the fuel part. As I said, the major ingredients of fuel and fuel plus oxidizers are form the propellant. So, the nitrocellulose form the fuel part, whereas the nitroglycerin, they form the oxidizer part. Now, depending on the nitration, the degree of nitration, the nitrocellulose part, I mean the molecular structure of the NC may actually change, because this is basically the cellulose which consists of carbon, hydrogen, oxygen in the structure. They are substituted with some nitrate radical or NO3 radical, and that will give the molecular structure of the nitrocellulose. Now, depending on the nitration, as I said, this structure will depend. Now, similarly, the glycerin or the propanediol, that is also replaced with NO3 radical to form the nitroglycerin. Now, both the nitrocellulose and nitroglycerin can act as single propellant, because they have the capability of to act as both fuel and oxidizers. However, for double base propellant, the nitrocellulose part is acting as the fuel, whereas the nitroglycerin part is acting as the oxidizer. Now, once they mix together, they are going to form the double base propellant. And sometimes it is known as the homogeneous propellant, because they are intermediately homogeneous propellant, because they are mixed intermittently. Sometimes plasticizers are also used in a small quantity in the double base propellant to improve the fluidity of the propellant and the processability of the propellant. So, it is not that in case of double base propellant no other ingredients are used, rather small amount of plasticizers are also used in double base propellant. Of course, still they will not affect the homogeneity of the propellant. That is why the double base propellant are also called the homogeneous propellant. Now, coming to the heterogeneous propellant, the heterogeneous propellant mainly consists of the solid crystalline oxidizer plus the polymeric binder. Now, it can have some aluminum particles as fuel as well, but mainly it consists of like the solid crystalline oxidizer and polymeric binder. So, in that sense the AP or the ammonium perchlorate is the common solid crystalline oxidizers, and the HTPB or hydroxyl terminated polybutadiene is the polymeric binder. So, they are going to form one of the heterogeneous propellant, or they are going to call the composite propellant. Okay. So, it may have aluminum particles within the propellant matrix. So, they are called composite propellant. Now, typical percentage of oxidizers may be like 70% oxidizers plus 10 to 12% of HTPB plus around 18% of aluminum. So, aluminum particles are fuel, 10 to 12% HTPB are going to be binder, and AP will act as oxidizers. So, this type of propellant is called composite propellant, and it is very much part of the heterogeneous propellant, because it is containing the various solid crystals and the solid spherical aluminum particles, which is going to create the heterogeneity in the propellant matrix, and they are called the heterogeneous propellant. So, this is the most common example of heterogeneous propellant. Now, in order to improve the performance of the double base propellant, sometime additional amount of oxidizers is added in order to improve the performance of the double base propellant. So, if we add AP to double base propellant to improve the performance, improve this specific impulse, this is called composite modified double base propellant, or sometime it termed as CMDB, composite modified double base. So, what additionally we are adding, NC plus NG was the main ingredients for double base propellant. Now, we are adding some amount of ammonium perchlorate to improve its performance, and they are going to form. So, since you are adding some solid crystals, so AP is solid crystals. So, we are actually not maintaining the homogeneity of the double base propellant. So, it is becoming heterogeneous, that is why, and it is kind of like a composite propellant. So, it is becoming like composite modified double base propellant. So, this is the basic formula, basic ingredients for composite. Now, it can have like some amount of HMX or RDX also. Instead of, it does not mean that it always have like AP as the additional oxidizer, it can have like HMX or even RDX, that is also comes under the category of composite modified double base. So, basically we are changing the composition of the double base propellant by adding some additional oxidizers. So, these are like some organic oxidizers or some inorganic oxidizers, which are added to the double base propellant matrix in order to improve the performance. So, this is CMDB. The other category of propellant is called nitramine propellants, which we have already told ourselves during the discussion of the oxidizers. So, basically the HTPB plus HMX or RDX. So, some binder and any of the organic oxidizer, if they are added together, they are going to form the nitramine propellant. As we already know the name now, by now, the hard majesty explosive, and this is like R&D explosives, which we already discussed in the previous class. This is like tetramethylene tetranitramine, and this is cyclo tetramethylene tetranitramine, and this is like R&D explosive, which is tricyclotrimethylene trinitramine. once we add these nitramine type of oxidizers to this binder, we are going to form the nitramine propellants. Now, remember this during the combustion, this hydrocarbon gases formed from the polymer is going to combine with these fuel rich products of HMX or RDX to form low temperature products. Now, here we need to remember that it will have like few oxidizing radicals and the binder surrounding nitramine crystals cannot fully oxidize. So, sometime it will so happen that the binder is going to decompose at the combustion temperature and is going to form the gases rich with hydrogen and carbon monoxide, which is going to reduce the molecular weight. So, that will cools the combustion chamber temperature, but is going to have like mostly H2 plus CO as the gaseous products. Sometime the propellant formulations in addition to like HMX and RDX, some small amount of AP is also added to the nitramine propellant just to improve the performance of the nitramine propellant, and this type of propellants will have applications mostly in the strategic side. So, it has applications in the strategic area. Sometime as high as like 85% of the oxidizers are added to this type of polymeric binder to form the nitramine propellant. So, it is actually highly solid loaded propellant. Sometime AP is added to improve the performance. Okay, so these are the major classification of the solid propellant. Now, we can talk about the other type of some other type of propellant. For example, like gas generator propellant. Okay, what are the other type of other propellant categories? So, major categories we have said like homogeneous propellant and heterogeneous propellant based on the mixture of the fuel and oxidizers, but based on the applications there are other propellant categories. For example, like we can have gas generator propellant. So, the main motive of gas generator propellant is to produce hot gas, but not thrust. So, this type of propellant are not thrust. So, they are going to produce hot gas, not for producing that. They usually have low combustion chamber temperature, low TC of the order of like 800 to 1600 Kelvin. So, their purpose is to different applications, not like for launching the any kind of satellite launch vehicle, not like that. So, they are having different type of applications. The typical ingredients for this type of propellants are like this. It can have like ammonium nitrate, let us say it can have like 78% of ammonium nitrate. It can have like some polymeric binder, let us say HTBB or any kind of polymeric binder, which will takes about 17%. It can have some additives like processing aids, for example, like plasticizers, some processing aids, stabilizer, that may contain like 5% of that. Oxidizers typical size may be like 150 to 200 micron. Now, if you look at the combustion side, the combustion products is going to form typically like carbon monoxide, it can have carbon dioxide, it can have nitrogen, it can have hydrogen, it can produce some amount of methane, etc. So, these are the typical combustion gases, and the temperature flame temperature will be in the range of like 1400 Kelvin. So, they are not intended for applications where thrust is the prime objective, rather it is going to produce hot gas by burning the different propellant ingredients. Okay. So, this is like another category is called gas generator propellant. Other category of propellant is called smokeless or reduced smoke propellant. Smokeless or reduced smoke propellant. So, generally this, if we have aluminum particles in the ingredients, they will form like Al2O3 aluminum oxide, and they are very smoky. If we add aluminum particles into the fuel into the propellant matrix, they are kind of very smoky in nature, like the exhaust products are very smoky. In fact, if you use some kind of burn rate modifier like aluminum, zirconium or iron oxides or any kind of metallic species, generally they form like visible cloud trails or small solid metal or metal oxide particles in the exhaust. So, they are going to form some smoky exhaust. So, if you have metallic species in the ingredients, they will give the smoky exhaust. So, there are certain military applications where we need to have smokeless or even reduced smoke propellant. So, that type of category is called low smoke or minimum smoke propellant. So, it will almost have like a faint faintly visible flame, faintly visible flame. So, this is fine applications in mainly like military applications, where smokeless exhaust will help in dodge the enemy's radar, or it will not be easily detected by the enemy's radar. So, there are different kinds of oxidizers have been tried or even have been researched on just by looking at how to minimize the exhaust smoke. For example, like if we do not use any kind of solid particles within the double base propellant matrix and modify with some HMX or even RDX, this may actually give very few or even no solid particles in the exhaust. So, like we can have like DB propellant plus modified with HMX, this going to give us no solid exhaust. That may fairly have like a reduced or low smoke propellant, because they are not containing any kind of aluminum particles there. If we use some AN composite propellant, ammonium nitrate composite propellants, they are also going to give like low smoke propellant. So, this is category of propellant based on the applications. The other type of propellants we can also need to know is the igniter propellant. We will remember that, see, the propellant, once it is there, we must need to ignite it using some igniter. Okay. So, we have the igniter here. So, igniter plumes will be created. So, there are certain category of propellants where the choice of propellant is depend on the applicability. For example, like for the igniter, we need to have like very fast high heat release or high gas evolutions, so that it can actually give the plume hot plume to the propellant surface and is going to ignite it. Of course, it needs to have like a stable operation or stable initiation of the ignition. It can operate over the required ambient temperature range. Of course, it need to have good aging characteristics as it is required for the general propellant characteristics. Low cost ingredients, low fabrication cost, the sensitivity of the burn rate to ambient temperature changes should be low. So, these are the normal thing, but the major thing is that it needs to have like a fast high heat release and high gas evolution per unit ignited propellant mass, because that is the main objective of the ignited propellant. So, these are the certain category of propellants where the propellants are used for igniter composition. For example, like some amount of boron particles are used as the fuel for ignited propellants. So, one such common example of ignited propellant is like this: boron plus boron plus potassium nitrate. This is the common example of ignited propellant with some binder. Like boron particles can be like 20 to 30%, it will have 20 to 35%, it will have like 65% of KNO3 and some small amount of binder, that is going to form the ignited propellant. There are other ingredients have been tried to form the ignited propellants. The main objective is to produce the high heat release at a faster rate. Okay. Now, the binder typically may include like epoxy resins, it may have like graphite or even vegetable oil or nitrocellulose as the binder, but the common fuel is kind of a boron particles and the oxidizer is potassium nitrate. So, these are the various category of propellants we have talked about, like starting with the homogeneous propellants, then heterogeneous propellant, then based on the applications we have smokeless or reduced propellant, reduced smoke propellant, we have the gas generator propellants. For example, like there are common application of propellants is in the car bag, airbags in the car, where the high gas is to be evolved, has to be evolved within a very fraction of time or even a fraction of second, because when there is a heat on collision, like during a high, while the car is proceeding or running with a very high speed. So, there is a very minimum amount of time is required to inflate the airbag. So, the only option is that some kind of a propellant which can get activated once the collision occurs, and it will inflate the balloon, which will actually protect the passengers and the drivers from the injury. So, the common application of gas generator propellant is there in the airbag. The military applications, the smokeless or reduced smoke propellants are used, and then another category we have discussed is the ignited propellant, where the composition is mainly used for the high heat release at a faster rate. So, common ignited propellants we have said like it is a combination of boron as the fuel and potassium nitrate as the oxidizers. Typical percentage is like 20 to 30% of boron and 64 to 65% as the potassium nitrate, and some amount of binder is of course used to hold the both the boron particles and ammonium and the potassium nitrate oxidizers. Okay. With that, I think we closed our discussion on the propellant ingredients. Now, we will try to solve some numerical problems on the mixture ratios, the fuel rich side, fuel lean side, or rather we said like the oxidizer side, oxidizer rich, fuel rich propellants, how to really get into the numbers about different polymeric fuel such as HTPB, like the common binder, and some ingredients like ammonium perchlorate oxidizers, fuel like aluminum particles. So, we will try to solve some numerical problems on this thing, and then you will be pretty much okay with the chapter. All right. Thank you so much.